The steel groans, a sound no human should ever hear a bridge make. You cannot stop. You cannot turn around. The car ahead of you vanishes behind a wave in the pavement. This is not a nightmare. This actually happened. On November 7th, 1940, at 11 o'clock in the morning, the Tacoma Narrows Bridge danced itself to death. When it opened on July 1st, 1940, the Tacoma Narrows Bridge was a triumph of ambition. It was the third longest suspension span in the world, stretching 5,939 feet across Puget Sound in Washington state. It linked the city of Tacoma to the Olympic Peninsula, a vital artery for commerce and travel. The designer, Leon Moisseiff, was the most respected bridge engineer of his generation. He had helped design the Manhattan Bridge and the Golden Gate. He believed in slender, elegant spans, and the Tacoma Narrows was his masterpiece, or so everyone thought. From the very first day, the bridge had a problem. Even a gentle breeze made the deck undulate like a flag in the wind. Motorists reported seeing the car ahead disappear behind a wave in the road. Passengers got seasick. The motion was so pronounced that people drove hours out of their way just to experience it. Locals nicknamed it Galloping Gertie, and for 4 months, that was just the way things were. A quirk, a curiosity, nothing to worry about, or so the engineers said. Engineers tried to fix the motion. They installed hydraulic dampers, shock absorbers for the bridge, to calm the bouncing. They added cable ties to restrain the swaying. They bolted down sections of the deck. Nothing worked. The bridge kept galloping. But here is the strange part. Nobody thought it was dangerous. They thought it was just a quirk, an annoyance, a bridge with a personality. After all, suspension bridges had been built safely for over a century. What could possibly go wrong? On the morning of November 7th, 1940, the wind was not particularly strong, only 40 miles per hour. The bridge had survived stronger winds before, but something was different this time. The bridge began to twist. Instead of the usual up and down galloping, the deck started rotating along its center line. One edge rose while the other fell. The road became a ribbon of steel twisting through the air, a motion nobody had ever seen a bridge make before. This was not galloping. This was torsion, and torsion is fatal. The phenomenon that killed the Tacoma Narrows Bridge is called aeroelastic flutter. It is what happens when wind feeds energy into a structure faster than the structure can dissipate it. Imagine pushing a child on a swing. If you push at exactly the right moment, the swing goes higher and higher. The wind did the same to the bridge, but there was no one to stop pushing. Each twist made the next twist worse. The amplitude grew and grew. The bridge was literally resonating with the wind, and it could not stop itself. Most people think the bridge collapsed because of resonance, the same phenomenon that shatters a wine glass at the right frequency. But that is not quite right. Resonance is when an external force matches a structure's natural frequency. Flutter is more dangerous. It is a self-feeding loop. The bridge's motion itself created the aerodynamic forces that made it move more. The structure and the wind were no longer separate. They had become one system, a system feeding on its own destruction. A University of Washington engineering professor named F.B. Farquharson was monitoring the bridge that morning. He had been studying its motion for months. When he saw the deck begin to twist, he grabbed his 16mm movie camera and ran onto the span. He filmed from the anchorage. He filmed from the tower. He filmed as the road beneath him tilted 45 degrees. His footage captured every second of the collapse. It would become the most famous engineering film in history, and the most painful to watch. At 10 a.m., the center span began to tear apart. Steel suspender cables snapped like guitar strings, one by one, each with a sound that witnesses described as a gunshot. Concrete cracked and fell into the water hundreds of feet below. The bridge did not just collapse. It came apart piece by piece, every minute worse than the last. Leonard Coatsworth, a newspaper editor, was driving across with his dog. He made it to the tower. Then he had to make a choice. Remarkably, only one life was lost that day. A black cocker spaniel named Tubby. Leonard Coatsworth had been driving across the bridge with Tubby in the passenger seat. When the deck tilted 45 degrees, Coatsworth crawled out on his hands and knees. He tried to go back for the dog. Twice. The bridge was too unstable. He watched his car slide across the tilted deck, crash through a safety barrier, and plunge into the gorge. Coatsworth later said the worst moment was hearing Tubby howl as the car fell. The dog became the lone casualty of the most documented bridge collapse in history. At 11:02 a.m., the main span gave way. 2,800 feet of steel and concrete, the entire center of the bridge, plunged into Puget Sound. The sound of the impact was heard over a mile away. When the dust settled, the towers still stood. Framed against the gray November sky, they looked like a monument to everything that had gone wrong. The bridge had collapsed in just over an hour. From first twist to total destruction, 62 minutes. A structure that took 2 years to build, gone in a single morning. The collapse sent shockwaves through the engineering world. This was not a failure of materials. The steel did not crack. The concrete did not crumble. The design itself was wrong. Suspension bridges had been built for over a century. How could a moderate wind of 40 miles per hour destroy a brand new bridge? The news made front pages across America. Insurance adjusters rushed to the scene. Lawsuits were filed. And in every engineering department across the country, professors tore up their lesson plans. Everything they thought they knew about bridges had just collapsed into Puget Sound. The answer changed engineering forever. The bridge was too flexible. Its deck was too light and too narrow. It lacked the stiffness needed to resist aerodynamic forces. But the deeper problem was worse. The design had never been tested for wind at all. Not in a wind tunnel. Not in any simulation. Leon Moisseiff had calculated the static loads, the weight of the deck, the cars, the snow, and assumed that was enough. He never considered that the wind could interact with the bridge dynamically, that a structure could become an instrument played by the air itself. Before Tacoma Narrows, bridge design was about static strength. How much weight can the deck hold? How much force can the cables take? Engineers thought of bridges as fixed, rigid objects. After Tacoma, they understood that every bridge lives in a river of air. Wind flows around a deck the same way water flows around a boulder. And if that flow creates vortices, invisible whirlpools of air, the bridge will dance. The question is not whether it will move, but whether the movement will tear it apart. Today, every major bridge in the world undergoes wind tunnel testing before a single ton of steel is ordered. Engineers build scale models and subject them to hurricane-force winds. They study flutter. They study vortex shedding. They study torsional instability. The legendary aerodynamicist Theodore von Karman, who analyzed the Tacoma footage, helped create the science of bridge aerodynamics from the wreckage. Every time a new suspension bridge is built, the engineers ask themselves one question: is this going to be another Gertie? The replacement Tacoma Narrows Bridge opened in 1950. It cost $14 million, more than double the original. It was wider, heavier, and had a stiffening truss underneath the deck that made it 8 times more rigid. It also had open steel grating in the road surface. The grating let wind pass through instead of pushing against the deck. The new bridge was not elegant. It was not slender. It was ugly by comparison. But it has stood for over 70 years through countless storms. It is a monument to humility, built on the bones of its predecessor. The original bridge cost $6 million to build. The insurance payout was only $4 million. But the real cost was not measured in dollars. It was measured in shattered confidence. An entire profession had to confront the fact that its most respected principles were wrong. Leon Moisseiff never fully recovered. His reputation was destroyed. The deflection theory, his life's work, was discredited overnight. The Tacoma Narrows Bridge taught engineers a brutal lesson that echoes in every textbook today. Nature does not care about your calculations. Every suspension bridge you drive across today exists because of Galloping Gertie. The Golden Gate Bridge, which was retrofitted with bracing after the collapse. The Verrazano Narrows in New York, tested in wind tunnels for years before it opened. The Akashi Kaikyo in Japan, the longest suspension span in the world, designed with aerodynamics as the primary concern, not an afterthought. They all carry the DNA of that failed span. The bridge that danced itself to death saved countless lives. Not because it was strong, because it was weak, and we were brave enough to learn from it. So the next time you cross a long bridge and feel the wind against your window, remember the dog named Tubby, who became the single casualty of a bridge that was too confident in its own design. Remember the professor with his movie camera, capturing a profession's humbling in real time. And remember that sometimes, the greatest lessons come from the most spectacular failures. The bridge that danced itself to death did not fall in vain. It taught us that humility is not weakness. It is the only foundation strong enough to build on. This is Atlas engineered. So the next time you cross a long bridge and feel the wind against your window, remember the dog named Tubby, who became the single casualty of a bridge that was too confident in its own design. Remember the professor with his movie camera, capturing a profession's humbling in real time. And remember that sometimes, the greatest lessons come from the most spectacular failures. The bridge that danced itself to death did not fall in vain. It taught us that humility is not weakness. It is the only foundation strong enough to build on. This is Atlas engineered.